Much of the content in this video comes from pages 5 through 10 of your textbook and is meant to help you achieve learning objective number 4, which is to list the major gases composing Earth's atmosphere and identify the components that are most important meteorologically. Further, accomplishing objective 4 requires that you are also able to explain why ozone depletion is a significant global issue. In a moment, I'll ask you to pause the video and complete a very brief assignment. If you have not done so, it would be a good idea to skim pages 5 through 10 before you watch the rest of the video, paying particular attention to the bold words, which should include the key terms listed here, and to the figures and their captions. Please plan to read the content more thoroughly before you attempt the online vocabulary quiz or the concept quiz for this chapter. The air we breathe is a stable mixture of about 78% nitrogen and 21% oxygen, nearly 1% argon, and small amounts of gases like carbon dioxide and water vapor. Looking at this picture, jot down a few ideas about what else might be in the atmosphere. Also, make a few notes about how you think these additions may influence weather and climate. Pause the video now to complete this assignment, remembering that it's just meant to be a quick brainstorm activity. Don't let it take over your life. If you are completely stumped, reread pages 5 through 10 in the text and come back to this. So pause the recording now and jot down your answers. As I said on the previous slide, the air that we are currently breathing is 78% nitrogen, about 21% oxygen, and nearly 1% argon. We also have carbon dioxide and water vapor mixed in. But looking at this figure, which is a portion of table 1.1 from your textbook, I want to explain some of the supporting terms here. The first half of the table that isn't shown in this slide pertains only to the permanent gases. So you can see I put the big ones up there in the top left-hand corner of this slide. Those numbers are not likely to change much at any given location from one day to the next because they have very long residence times in the atmosphere, and because they are listed for samples of completely dry air. So in a lab, that means the water vapor has been removed, and we're talking only about clean and dry air. I'll say more about this idea in a minute when we talk about water vapor. The first three gases, nitrogen, oxygen, and argon, together comprise about 99.96 of a dry sample of air. Adding the other four gases in the first half of the table only increases that number to 99.962. So it's 0.002%. The second half of the table is shown in this slide. And at least in my mind, this is where things become a little bit more interesting. So these gases and particles are measured as a fraction of the total sample, not just the dry sample. So we haven't evaporated the water here or ignored the water. These all have very short residence times in the atmosphere. And that means when they appear in the atmosphere, a given molecule may be there for time periods ranging from 10 days in the case of water vapor to as long as 10 years for carbon dioxide and methane. CFCs, or chlorofluorocarbons, are added to the atmosphere by human beings. And they've only been added since about the middle of the 20th century. They have the longest residence time in the atmosphere in this whole list. They are still present in the atmosphere 80 years after their first addition. And it's interesting to note that these components are all part of the global climate change discussion. So everything in this part of the table are of some interest to climate scientists. The first four, water vapor, carbon dioxide, methane, and nitrous dioxide, are in fact greenhouse gases. The concentration of water vapor, you'll see here, can vary from near 0% to as high as 3 or 4%. And it has a global average of between 2 and 3%. So in a reality, if we recalculate these minor gases or variable gases as part of the total sample, we'll see that they make up a much larger percent of what's in the atmosphere than you might intuit by looking at the first half of the table. Even though the average abundance of water vapor is in fact greater than that of argon, it's not considered to be the third most abundant gas because it changes on a daily basis due to its very short residence time. In many locations, though, water vapor is in fact the third most abundant gas in the air. Most of the year in arid climates, deserts or polar regions, argon is in the third position and water vapor is fourth. Water vapor as a gas is invisible. Clouds are visible because they are made up of small drops of liquid water or solid crystals of ice. So when you see a cloud, you're not seeing the water vapor. You're seeing a droplet or a crystal. Water is the only compound that exists naturally in solid, liquid, and gaseous phases in the atmosphere. We'll spend more time talking about it because it's so important to not just weather phenomenon, but Earth's surface processes, which is really my main interest in science. And I'll show you a reason, one of the reasons why that occurs in a future video. Earth's original atmosphere was probably just hydrogen and helium, because these were the main gases in the dusty, gassy disk that formed around the sun before the planets really solidified and came into beings as individual entities. The Earth and its atmosphere were extremely hot. So the molecules of hydrogen and helium, because of the high temperature, were moving extremely fast. And so fast that they eventually all escaped Earth's gravity and drifted into space. So the second atmosphere, the young Earth atmosphere, came from within the Earth itself. And it was generated by volcanism as the Earth's solid crust continued to form. Outgassing is the jargon term, an important one for our class. Outgassing from the volcanoes added three main components to the atmosphere: water in the form of steam, water vapor, carbon dioxide, the CO2 in this picture, and ammonia. As the Earth cooled, water vapor condensed, right? It turned from a vapor to liquid droplets and formed clouds. And when that happened, torrential rains began to fill in all the low-lying areas on the planet, and those became our oceans. In those oceans, nearly 3.5 billion years ago, photosynthesizing bacteria began to release oxygen into the water. During photosynthesis, organisms use the sun's energy to produce organic material. Those are energetic molecules of sugar containing hydrogen and carbon. So they're taking what's available, the CO2 and the sunlight, and they're turning it into something they can use to sustain themselves, a sugar. And the first bacteria probably didn't use water because it wasn't around in meaningful ways. It probably used hydrogen sulfide, or H2S, as the source of hydrogen rather than water. One of the earliest bacteria, cyanobacteria, and we used to call this blue-green algae, but now we mean something else when we say blue-green algae. Cyanobacteria began to produce oxygen as a byproduct of photosynthesis. A possible early source, when we get to the current Earth atmosphere, the atmosphere that we have now may have gotten some of its nitrogen by disassociating the ammonia molecule. So if you look in atmosphere number 2, you'll see NH3 as one of the components. So one theory about how the nitrogen came about in today's atmosphere is that the N's became separated from the H3s. And those hydrogen molecules, being so light, just rose up and drifted off into space, just like they did in the early atmosphere. That's one possible explanation from where the nitrogen comes from. Earth scientists and atmospheric scientists are still interested in this. But remember that most of the modern atmosphere consists of a nitrogen gas, and that's an inert gas. It doesn't react easily with other elements. And it's not likely that all of the NO2 in our atmosphere came simply from disassociating ammonia. Recently, in a 2014 Geosciences Nature article, one Earth scientist suggested that it derived from the Earth's upper mantle. So where you can see in the right-hand part of this slide, a convergent boundary. These are two of Earth's lithospheric plates, an oceanic lithosphere and a continental lithosphere converging or colliding. And because the oceanic lithosphere is more dense than the continental lithosphere, it subducts beneath the continental lithosphere. So the tan area in this block diagram, I guess there's a few different shades of tan, but I'm talking mostly about this area in here is the upper mantle. And it's an area where the lithosphere is moving around, flowing. It's ductile. It moves around. In this portion of the Earth's outer layers, the nitrogen exists in an oxidized state. So down this slide here, we see ocean water coming in. We see sediments that have been up on the continent up here falling in, And this is a place where the mantle is exposed to a certain amount of oxygen. And when that happens, we see N2, the nitrogen gas, in the mantle fluids. And it's really easy to bring that fluid to the top with the N2 inside it and add huge amounts of nitrogen to the atmosphere. So it may be the case, at least one scientist says, looking at the different isotopes of nitrogen that are in the atmosphere, that a large proportion of our current nitrogen comes from these subduction zones, convergent boundaries. So that means there had to be plate tectonics before much of the nitrogen we see in the atmosphere came about. So it hasn't been around as long as maybe we used to think. But once it's free in the atmosphere, we can see this is a cartoon of the nitrogen cycle on this side of the slide. You can see that there are a bunch of different processes that help maintain that 78% nitrogen in the atmosphere. So living things, it's a key component of a lot of living things. Animals, as they die, they provide nitrogen to the soil, but they also do it while they're alive through urine and feces. The decomposers will turn that nitrogen into a different state. So we might see ammonia. This isn't the ammonium I was talking about in the atmosphere. This is an NH3. This form can change state underground. We'll see nitrates stored in the soil and eventually come back up to the surface through the roots of plants and help to establish relatively constant levels of nitrogen in the atmosphere. Water in the atmosphere. You're probably familiar with the term humidity on TV weather reports. Humidity is a reference to the amount of water vapor in the air, and we're going to go into that in much greater depth in a future chapter. There are several ways to express the humidity in the air. The amount of water vapor that is in the air, as I said before, varies considerably from 0 to 4%. Why is such a small fraction of the atmosphere so significant? It's because the fact that water vapor is the source of all clouds and precipitation would be enough, all right, to just explain its importance. However, water vapor also does some different things. Like carbon dioxide, water vapor absorbs heat given off by the Earth, as well as some of the solar energy coming in from the sun. It's therefore important when we examine the heating of the atmosphere and the movement of energy on Earth. When water changes from one state to another, it absorbs or releases heat. That energy is called latent heat. It means hidden heat. As we will see later, water vapor in the atmosphere transports the latent heat from one region to another and is the energy source that helps drive many storms. Carbon dioxide is a gas that's only present in very minute amounts in the atmosphere. So it's 0.04 of a percent, or 400 parts per million. It is nevertheless a meteorologically important constituent of air. Carbon dioxide is of great interest to meteorologists because it's an efficient absorber of energy emitted by the Earth. And it therefore influences the heating of our atmosphere. Although the proportion of carbon dioxide in the atmosphere is relatively uniform from one place to another, and also at different heights in the atmosphere, its percentage has been rising steadily now for more than a century. The graph on the left doesn't go back quite that far, but it shows the growth in atmospheric carbon dioxide measured at the Mauna Loa Observatory in Hawaii since 1958. There's been a consistent increase since monitoring began. Much of this rise is attributed to the burning of ever-increasing quantities of fossil fuels, such as coal and oil. And it's why we really don't dispute the fact that CO2 concentration is increasing. It's at a higher level than we would like it to be. And that is not really an issue that any scientists dispute. Some of that additional carbon dioxide can be absorbed by water in the ocean or used by plants, but more than 40% of what's up there remains in the air for longer time periods. Estimates project that by sometime in the second half of the 21st century, carbon dioxide levels will be twice as high as pre-industrial levels. So when we talk about pre-industrial levels, we're talking way back there. So here is 1800, and you can see a small spike, a small increase in this curve here, going back to the early part of the 1800s. But when we got really good at manufacturing with the steam engine and in big plants, boy, we really started adding CO2 to the atmosphere. So this is the Industrial Revolution, started in England and maybe perfected in the United States. And nowadays, we're looking at other parts of the world that are in that industrial mode. We're trying to do things to reduce the amount of CO2 that's released into the atmosphere because of the dramatic influence the CO2 has on weather. Most atmospheric scientists agree that increased carbon dioxide concentrations have contributed to a warming of Earth's atmosphere over the past several decades and will probably continue to do that in the decades to come. The magnitude of such temperature changes is still uncertain, and it depends partly on the quantities of CO2 contributed by human activities in the years ahead. One other thing about this graph I'd like to mention is that we can see it has ups and downs. I'd love it if you paused the video now and thought about why that might be the case. I'm going to pause just for a quick second, and while I take a sip of coffee, you guys pause and think about it. What's a good explanation for that? The answer is photosynthesis, the process by which green plants convert sunlight into chemical energy removes carbon dioxide from the air. In spring and summer, vigorous plant growth in the extensive land areas of the northern hemisphere removes atmospheric CO2, so the graph takes a dip. As winter approaches, many plants die or shed leaves. The decay of organic matter returns CO2 to the air, causing the graph to spike upward. So you can see that the reservoir of atmospheric CO2 comes from dissolving of CO2 in the water, the burning of plants, from respiration by animals and humans, that's this arrow, from volcanic activity, certainly, and from fuel combustion, among some other probably less significant sources. What draws the CO2 out of the atmosphere, the reason why we see down turn in the average amount of CO2 in the atmosphere is that we have a lot of photosynthesis, a lot of chemical weathering. That's the decay of rock material on the surface of the planet. And we also see a dissolution of CO2 by marine life. A quick word here about aerosols. I always get nervous when I say quick, because sometimes these aren't so quick. The movements of the atmosphere are sufficient to keep a large quantity of solid and liquid particles suspended within it. Although visible dust sometimes obscures the sky, these relatively large particles are too heavy to stay in the air for very long. Still, many particles are microscopic and remain suspended for considerable lengths of time. They may originate from many sources, both natural and human-made, and they include sea salts from breaking waves. They include fine soil blown into the air, smoke, soot from fires, pollen and microorganisms lifted by the wind, ash and dust from volcanic eruptions, and many more sources too. Collectively, those tiny solid and liquid particles are called aerosols. And the first image here on the left shows two examples of aerosols. First, there's a large dust storm blowing across the northeastern China towards the Korean Peninsula. So that's this mass of dust. Okay, so that's a natural event. That's meteorology in action. But the second thing you'll see is a dense haze in this area that comes from an urban part of China. That's human-generated air pollution. We can see on the surface, when we have a day with very high aerosol content, we'll see the atmosphere looking like the picture on the right. Dust in the air causes sunsets to be spectacularly colorful. We think this was the case in the year without summer back in I think it was the 1780s. Just about 3 weeks of warm weather in the middle of August, and that was it for the summertime. Probably related to volcanic eruptions going on in big ones all across the Pacific Rim. Aerosols are most numerous in the lower atmosphere nearest to their primary source, which is the Earth's surface. Nevertheless, the upper atmosphere is not free of them because some dust is carried to great heights by rising currents of air, and other particles are contributed by meteoroids that disintegrate as they pass through the atmosphere. From a meteorological standpoint, these tiny and often invisible particles can be significant. First, as we'll see later, many act as surfaces on which water vapor can condense. That's a critical function in the formation of clouds and fog. Second, aerosols absorb or reflect incoming solar radiation. Thus, when air pollution episode is occurring, or when ash fills the sky following a volcanic eruption, the amount of sunlight reaching Earth's surface can be measurably reduced. Finally, aerosols contribute to an optical phenomenon that we've all observed, which is the beautiful red sunset. And after the 1980 eruption of Mount St. Helens, I was 11 years old, and we were living in Delaware, but we could see spectacular orange-red sunsets following that eruption because of all the new particles, the new aerosols that were out in the atmosphere. The last major component to talk about is ozone. And there are really two different ways to think about ozone. It's a form of oxygen that combines 3 oxygen atoms in each molecule. So its formula is O3, not O2. O2 is the gas. Ozone is not the same as the oxygen we breathe. That oxygen, the one that we can breathe, is O2. There's very little ozone in the atmosphere. Overall, it's just 3 out of every 10 million molecules. Moreover, it's not uniformly distributed across the globe. In the lowest portion of the atmosphere, ozone represents less than 1 part in 100 million. It's concentrated in a layer called the stratosphere, between 10 and 50 kilometers above the Earth's surface. In this altitude range, oxygen molecules are split into single atoms of oxygen when they absorb ultraviolet radiation emitted by the sun. Ozone is then created when a single atom of oxygen and a molecule of oxygen 2, O2, collide. This must happen in the presence of a third neutral molecule that acts as a catalyst by allowing the reaction to take place without itself being consumed in the process. So this is a mouthful of science here, but it's an important thing to keep in mind. When we look at ozone, where it's concentrated, in that 10 to 50 kilometer height range, there's a really crucial balance there. The ultraviolet radiation from the sun is sufficient to produce some single atoms of oxygen, and there are enough gas molecules to bring about the required collisions. The presence of the ozone layer in our atmosphere is essential to those of us who live on land. The reason is that ozone absorbs the potentially harmful ultraviolet radiation from the sun. If ozone did not filter a great deal of that radiation, and the sun's UV rays were able to reach the surface of the Earth just in their undiminished form, then the land areas on our planets would not be uninhabitable for most life as we know it. That's anything that reduces the amount of ozone in the atmosphere could affect the well-being of life on Earth. Although it's concentrated, I keep saying 10 to 50 kilometers, that's 6 to 31 miles above the Earth's surface, it is very vulnerable to human activities. Chemicals manufactured by people break up ozone molecules in the stratosphere, weakening the shield against the UV rays. The loss of ozone is a serious global scale environmental problem. Measurements over the past 3 decades, we've been able to measure it since about 1979. But since about 1985, we've been doing a good job of it. And the 2 satellite images shown in this slide show ozone distribution in the southern hemisphere on the days in September 1979 and 2013, when the ozone hole was at its largest for the year. The dark blue shades over Antarctica correspond to the region with the sparsest ozone. The ozone hole is not technically a hole where there's no ozone present, but it's a region of exceptionally depleted ozone in the stratosphere over the Antarctic that occurs in the spring. Now, if you go look for other pictures of the ozone hole, for example, if you go back to 2010, you will see that the ozone hole, the blue area here, is much bigger than the 2013. That doesn't mean that the ozone hole problem is going away. It means that we had a particularly bad year in 2010. And the general trend is that the ozone hole over the South Pole has been, on average getting larger, even though it's smaller now than it was in 2010. We don't see the problem of ozone depletion going away, so we're still concerned about it. Another big difference, if you're able to find the September 2010 picture, these red areas where we do have a larger amount of ozone don't appear in that 2010 picture. I'll try to dig that up maybe and show it to you in class. But over the past 75 years, people have unintentionally placed the ozone layer in jeopardy by polluting the atmosphere. The most significant of the offending chemicals is one that's also in that table 1.1 that we saw at the beginning of this presentation. Those are chlorofluorocarbons, or CFCs. Over the decades, they were used as coolants for air conditioning and refrigeration equipment. Also as cleaning solvents for electronic components, propellants for aerosol sprays. I know that Aquanet was one that my sister used to have back in the 70s. And that hairspray was propelled by chlorofluorocarbons. So we've moved away from that. And I think most hair products, for example, don't have aerosol cans anymore. But those CFC propellants have been rooted out. So because the CFCs don't really react with anything in the lower atmosphere, those gases stick around for year after year after year and end up making it up into the ozone layer, where the sunlight separates the chemicals into their constituent atoms. The chlorine atoms released this way break up some of the ozone molecules. Because ozone filters out most of the UV radiation from the sun, a decrease in its concentration permits more UV wavelengths to reach the Earth's surface. UV radiation's most serious threat to human health is increased risk of skin cancer. An increase in damaging UV radiation also can impair the human immune system, as well as promote cataracts, a clouding of the eye lens that reduces vision and may cause blindness if not treated. And I remember being an undergraduate at University of Wisconsin and being interested in one of those kind of causes. The blindness in untreated vision reduction and cataracts is particularly common in third world countries, developing countries, where they don't have access to good medical care. Big sections of the Himalayan mountains have a very systematic problem with that kind of cataract. Okay, this is the last slide for this video. The concept check questions are meant to substitute for a review sheet. So in other words, you'll get review questions at the end of each lecture. So sometime during the time that this slide is shown on your screen, take a screenshot of it or copy down these questions somehow. This is your review set, your review sheet for the first midterm exam. So use the course content provided on the Canvas site as well as outside internet sources to verify that you can formulate answers to these questions. Your textbook is a great place to look for these. If you can comfortably answer these questions, you're in great shape. If you can't, review the textbook, rewatch the video, see if your abilities improve. If you're still completely stumped, why not start a discussion on the Canvas site? I'll visit that discussion board every day. You could also ask me for help directly, but odds are good if you have a problem with one of these questions, someone else does too. And so I'd be interested in knowing how those problems arise and how you guys are able to find help and resources. So always help me, tell me what your resources are, and I'll incorporate them into the class.